Hello, everybody, and welcome to another wonderful day of PChem. So today we're going to go ahead and be reviewing phase diagrams, but taking a little bit more time to focus in on one of our more familiar favorites, water. And it turns out that the water phase diagram is way more complicated than you probably previously thought. So when we look at the core portion of the phase diagram, so essentially, when water has a relatively low vapor pressure and essentially a moderate set of temperatures, we find our three common phases of water. We have our good old friend, liquid water. We also have water vapor, and we have solid ice. Now, as you may have noticed, ice is a little bit more confusing than you previously thought. So we actually label the ice that forms under these conditions as ice 1, essentially because it was the first type of ice discovered. And it turns out that these three phases have a triple point at our good old friend 0 degrees Celsius. Again, how we define 0 degrees Celsius. But then the question is, at what pressure does this happen? And it turns out that if I have ice and water in equilibrium, and water vapor is allowed to come to equilibrium, then we should be expecting the water vapor to be at about 6 millibar or 0.006 bar. So very low levels of, um, of water vapor present. And one of the important things to note is that as you go ahead and uh, apply more pressure, it turns out that we don't see too much movement going on in between ice and water. But indeed, if you actually look a little bit closer, we're actually going to find that increased pressure, as I increase the pressure on the system, the melting point is actually going to decrease a little bit. And we'll get into the math of why that happens a little bit later. But it's an important feature that is actually fairly unique to water. And again, as you would expect, as we go ahead and increase the temperature of the system, the vapor pressure of water ends up increasing essentially under an exponential curve until it reaches our critical point. And essentially past this point, at about 647 Kelvin and about 200 bar, at this point we now generate supercritical water, which will dominate this region over here. And again, this is actually some fairly good features of the water phase diagram. But one of the things that I do kind of want to remind people is that phase diagrams are much more complicated than we often think. Because as we stated previously, if I go ahead and have, say, ice, it can be defined by any 2 degrees of variance. So in this case, I may try and describe it with temperature and pressure. But that means I've uniquely defined volume. And similarly, with the gas, we often are looking at the temperature and pressure relationship, which again means that I've uniquely defined the molar volume. But it turns out we don't need to actually portray the relationship this way. Instead, we can actually look at a three-dimensional relationship, where instead what we do is we define the molar volume of the system and the pressure of the system, and I let temperature vary naturally. And it turns out that if you do this, well, we're back to our good old gas descriptions. And one of the reasons why our van der Waals gas broke down, because it wasn't able to describe the phase transition from liquid into gas. And this was exactly the reason why our ideal gas law broke down, is because the shape of the relationship in between volume and pressure gets a lot more weird the closer we end up getting to the water phase. And one of the reasons why is because we're actually starting to lose a degree of variance. So for example, if I know that I have a gas at a certain pressure, well, it turns out that then the liquid is going to be present throughout this whole time. While the molar volume of the whole sample itself ends up changing. So again, one of the things you should be aware of is that while we often describe our systems in terms of temperature and pressure, we can indeed expand the system to a full three-dimensional description by looking at the volume. However, at this point, we then automatically end up fixing the third variable, which is something you should be very aware of in practice. So let's go ahead and return to our good old pressure temperature phase diagram. So the phase diagram under these low pressure conditions is actually sort of fairly typical, with again, in these three regions of ice, liquid, and vapor, I can describe my system using one of the equations of state, and then the system is defined along the sublimation line, the vaporization line, and the fusion line by essentially these phase transitions. And we'll need to develop a set of equations this chapter describing where these lines are located. But as I said previously, just because I have, say, one phase of ice, that doesn't mean I might not have other solid phases of ice. And in fact, it turns out that ice has over 16 different phases. And these different phases of ice are represented by different allotropes. So the first discovered is our good old friend, ice 1. But we also say under low temperature conditions can form ice 2, or under intermediate temperature conditions, but again, very high pressures, can form ice 3, and as well as ice 5, 6, 8, 7, 10, 11, and there's several other ones out there, including if I go way down in this region, you can actually start forming ice 9. And this gives us a lot of different equilibrium that we in practice need to solve. And in truth, all of these ices are possible, but again, mostly under extreme conditions, as represented by the fact that we have a lot of different other triple points where we may have 3 different kinds of ices or 2 kinds of ices and liquid all being in coexistence. So for example, if I look at the ice 1, ice 3 water triple point, this one occurs at actually fairly moderate temperatures of 251 Kelvin, so only 22 degrees C, but at about 2.1 kilobar or 2,100 bar. So again, these are very extreme conditions, and you're only going to see it form under very high pressures. The ice 2, 3, and 1 phases occur, again, a little bit lower temperatures at negative 35 degrees C, but at similar pressures of about 2,130 bar. And as you work your way up, you're going to find these triple points at more and more kind of exotic conditions until, say, you start getting to the point of, say, ice 2, 5, and 6, which have a triple point at negative 70 degrees Celsius and 6,200 bar. And we haven't even gotten into the extreme conditions. So these are often studied when you're looking at, say, geological processes or under astrochemical situations where you can start getting very odd pressures and temperatures, much more than we would typically expect. And so this is often a very popular type of study when trying to study extreme conditions, because before you figure out how, say, rocks form, you first need to know what kind of ice might be forming them and what you might be dealing with. Now let's go ahead and take a step back from our classic thermodynamic description and look at more what's happening at an ice level, at a molecular level. So when we're talking about ice 1, so this is our room temperature ice, what we're often looking at is, say, ice 1H. And so this has a very nice sort of lattice. If you start going into lower temperature conditions, you can actually start forming slightly different forms of ice 1. Now, as I start, say, increasing the pressure of the system, what ends up happening is you're going to form this metastable ice 9 prime species with, again, several different ice 9s being possible. And what you're going to notice is that this has a slightly offset, kind of awkward lattice where I'm now starting to permeate one layer below another. And then you can compress this even more till you get to ice 15. And then as you compress the system even more, you get to the classic stable, very high pressure system. So you have to put a lot of high pressure to move past the semi-stable 9 and 15 to get to ice 8, which again is our low pressure scenario. And one way to view ice 8 is almost as two ice 1 lattices overlapping with each other. So again, very stable from a molecular interaction if you look at each individual lattice, but there's also a lot of repulsion that you pay for. And it takes a great deal of pressure to reach these conditions. So one of the other things I want you to be very aware of when we're talking about water is that it also has its own special terminology that we can apply to describe uh, its properties in terms of its phase transitions. So one of the important things to remember about water is that it turns out water very often isn't under equilibrium conditions. So if I have water vapor, it usually takes quite a while till that water vapor is now equilibrium with the water present. So instead, what we often do is describe the amount of water vapor currently present under any given condition in terms of its vapor pressure or what the system would look like under these equilibrium conditions, or another way of thinking about it, referencing that nice solid reference point of its phase transition. So one of the most common you've probably heard about is percent humidity. Scientifically, we often describe this instead as a ratio instead of percent as relative humidity. And so the way you can describe relative humidity is the current partial pressure of water over the vapor pressure or equilibrium pressure of water. And simply you'll just take the ratio of these two. So the current pressure has to be obtained from a measurement. This vapor pressure you're often going to need to determine by knowing uh, where that phase transition occurs. However, once you know where the vapor pressure is, you can back out what the relative humidity is simply by making your measurement. So again, this should hopefully make sense of a lot of weather reports that you've heard when people are talking about relative or percent humidities. And you'll notice that the vapor pressure will end up changing based on temperature. So what may be a high relative humidity on a cold day will be a very low relative humidity on a hot day. And this is really kind of illustrated when we look at another special term, which is the dew point. So this is essentially the temperature at which water will condense or deposit. And you can imagine this by looking at relative humidity. Let's say I start off with kind of a moderate relative humidity, and then the temperature drops. Well, as the temperature drops, we also would expect the vapor pressure to drop and the relative humidity essentially increases. Well, eventually it's going to increase to the point where it's at 100%. At this point, well, the air can't hold any more water, so it's either going to condense or deposit on a surface. Condense if it's below 0 degrees Celsius, deposit or form a solid if it's below 0 degrees. So one of the things you often end up looking for is when the air has a dew point that's lower than the temperature than the nightly lows. If that ends up happening, this is when you're going to expect to go out and find a lot of dew in the morning or frost on your windshields. So if you want to prevent frost buildup, look for drier air or a warmer or a spot that doesn't get quite so cold at night. Quickest way to help prevent frost. And again, one of the big things that we're going to need to do in order to determine either of these points is to know the vapor pressure, how vapor pressure is related to temperature. So next time, we're going to be starting to build up these relationships in between our phase transitions and changes in pressure and temperature. Till then, take care.